question. So, Physics Penguin and I were chatting, and she mentioned space-time diagrams. But I live in the ocean, not in space. So, what are they, and why should I care?
Oh, Burly Whale, that's a great question. And I'm so glad that you and Physics Penguin were chatting about this. That makes me so happy.
Okay, space-time diagrams fits right in with our learnings about relativity. So, what are they, and why should we care? Well, in relativity, we're dealing with we're dealing with a lot of weird stuff about time. And when we use our regular old handy dandy XY diagrams, it can be really tricky to show how things change over time. If I draw a diagram and then I'm like, I want to show a bird that is moving in space or moving in time, I would have to draw another diagram and show how that bird moved. And we actually did that in the last video. And I want to be lazy, not draw 14 representations of a bird. I will do that in art class or for funsies, but if I want to do these types of problems, I want to be lazy, right? Anyway, so a space-time diagram uses time on the vertical axis instead of space. So we have time up here, and then we have x on the horizontal axis. And this allows us to really focus on how events are changing in time without having to draw how the actual object might look different in time. And we can just use this basic diagram. Okay, but one key thing to keep in mind, we have x in meters and time in seconds. And this can make it a little bit tricky to compare things. Also, when we're talking about relativity, we're talking about things that are moving at or close to the speed of light. Very, 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 very fast. And the speed of light is a constant, c, which is 3 times 10 to the 8th meters per second. Very fast, 3 with 8 zeros after it, or 300 million meters per second. That's why we do this, because I want to be lazy and not draw that many zeros. Anyway, so very fast. And we also have this handy dandy, look, it's meters per second. If you have meters per second times seconds, you get meters. Oh, look at that. So if we multiply c by our time axis, we can actually kind of have a meter of time. And you're like, wait, what is that? So basically, this is the amount of time it takes light to travel 1 meter. It's very, very fast. So that would actually be, it's like 3.3 times 10 to the negative ninth seconds. So very, very, very fast. But like I said, when you're dealing with really, really, really fast particles, you are looking at very, very small time scales. And so by multiplying this factor and scaling our diagram like this, we can keep events in the away from the axes and kind of spread out throughout our diagram instead of all like clustered along the x-axis or clustered along the vertical axis, which makes it kind of tricky. Okay, so that's basically how we draw it, but what does this actually mean? How do we interpret this? It can be kind of weird and funky to think about something that is moving in time. Also, don't we live in a four-dimensional world? Yes, my dear friend, but I can't draw a 4D diagram, and I don't really want to try to draw a 3D diagram. So we're just going to focus on one dimension in space so that we can compare it with our one dimension of time. We do this a lot in physics because, again, we like to be lazy. Okay, so let's say we set up an experiment and we want to ask how different events are changing in time. So I'm like, okay, I have events. Oh, my chalk just rolled all the way off. I have an event A, I have an event D, I have an event B, and an event C. And we want to ask some basic questions. Okay, well, what's going on with A, B, C, and D? How and when do they occur? Now we need to interpret what this diagram means. And to do that, I'm going to grab my chalk that fell on the floor and use clocks to represent. Okay, so we're going to define our origin to be now. When we start our experiment, we're like, bing, this is now. This is the present moment. And let's say for funsies, we start our experiment at noon. So we need to set up multiple clocks so that we can make sure we are measuring the time, recording the time at different places appropriately. So all of our clocks along the horizontal line will be at the same time because they are at the same, well, they're at the same spot along our vertical axis, and so they're at the same time. As time progresses, our clocks will move forward in time. They will not move in space, right? Because we're not going to go and pick up our clock and move it somewhere else. But just by the passage of time, they will move forward in time up along the vertical axis. And if we happen to have a time machine, we could ask, oh, well, what would our clock look like if we moved backwards in time? And it would be like, oh, well, instead of at noon, it would be like at 11:50 or whatever. And then all of our clocks would show that because we could, at that previous time, we could like walk around and look at all of the clocks that are sitting stationary. So the clocks don't move, but time does. Pretty wild, right? We can move around in physical space, but we can't really control the passage of time. It continues to move forward. And this is a way for us to represent that. Okay, so now we can say, oh, yeah, well, what's going on with A, B, C, and D? Well, A and D occur at different times, right? Because A is at this time, D is at this time in the past, but they happen at the same physical location. So they will be recorded by this same clock. A and B happen at the same time, but different physical locations. Event A will be recorded by this clock, which will point to with a yellow arrow, and event B will be recorded by this other clock, which is a different physical location. And then C is all the way off on its own. C is happening before A, B, and D in time because it is at, oh, I'll use brown for this one. It is farther in the past along the time axis, and also it is at a different physical location than all of the other events. So C is our anomaly, I guess, I don't know. Or A, B, and D are having fun and related, and C is over there doing its own thing. Okay, so that is the basics of not world lines. We'll get to that in a sec. Space-time diagrams. Woo! Basically allows us to compare events over time with how they change in space, or how events in space change over time, more easily than having to draw a bunch of things. I drew a bunch of clocks right now, but that's really just to illustrate. The clocks are effectively implied in the spacetime diagram. Okay, I hope that is helpful. The thing that I do want to mention about world lines is that you can use spacetime diagrams to draw what are called world lines, or basically how particles travel in space. And then you can use that to figure out, will these particles ever interact? Or you can ask questions like, how far back in time can we see on Earth? And how far in the universe can we see? And it's kind of one and the same, because we can do this question. We can ask, well, how far can light travel over the age of the universe? And, at what point, if ever, will we be able to see that light? So really cool questions like that. If you want to get into world lines, please let me know. We can do that in the next video. Otherwise, please let me know if you have any questions about other topics in science, tech, engineering, and math, and we can continue to look at how weird and wonderful this universe is and how special it is that we are here and that we exist and that we can ask questions and learn things like this. All right. Thank you very much for joining me, friends. We'll see you next time.